In this function, we're going to look at exponential functions. So let's say you have 3 people infected with the coronavirus that's going on right now in the state you live in. But the number of people over the next few weeks are looking like below. So initially, there were 3 people infected, and then in the next week, there were 6. Next week, 12. The following week, 24. And by the end of the month, there were 48 infected. So based on that pattern in the table, can you guess what the last item should be? Well, if we follow the pattern, it looks like each week that goes by, the number of people are doubling, multiplying by 2. So by the time I get to the 5th week, I'm going to have, I guess, 96 people infected. Now, if we were to guess what equation would fit this situation, we would just keep track of what we just did. We ended up multiplying by 2 over and over and over. So we started with 3, and then we multiplied that 3 by 2, and then we multiplied it by another 2. So there's 1, 2, 2 2s, 3 2s, 4 2s, 5 2s. So we ended up multiplying that initial 3 people that we had by 2 5 times. And notice in the 5th week, I had 2 to the 5th. So with that, we can guess that if I keep going to t weeks, I'm going to have 3 people to start with still, and then I'm just going to keep stacking up powers of 2 over and over and over until I get to the tth week. That sounds funny, tth week. So in other words, here I would have 3 times 32, which gives me the 96 that I ended up with when I followed the pattern over and over. So the equation that we would guess for this model, I guess, would be P of t equals the 3 people that I started with, and then I kept doubling that, and I kept doing that over and over, depending on how many weeks t I went out. Now let's look at another similar problem related to what's going on now. Let's say at 6 a.m. there were 1,000 rolls of toilet paper on the shelf at Target, and then every second the number was recorded as below. So to start off with, there were 1,000 rolls, and then a second later there was only 500, and a second later after that 250, and 3 seconds later 125. So can you guess about how many rolls there would be for the 4th second? So similar to the previous one, I guess if we follow the pattern, it looks like I'm dividing by 2, or in other words, I could think of that as I'm multiplying by 1/2 to get from 1,000 to 500. Then I'm repeating that again, multiplying it by 1/2 to get to 250, and then multiplying it by 1/2 again to get to 125. So if I follow that pattern, either multiply by 1/2 or divide by 2, same thing, looks like I'm going to get to 62.5 rolls of toilet paper left after just 4 seconds, which sounds awfully familiar with what's going on right now, sadly. So we guess that that'll be 62.5. So let's say like if we were approximating, like maybe 62 rolls of paper would be left by the time we end up with the 4th second. Now, can you guess what the equation would be in this situation? Well, the same thing that I did before happened here. I started with 1,000 rolls, and then I multiplied that 1,000 by 1/2 to get to the next one, and then another 1/2 to the next one, another 1/2 to the next, and by the time I got to the 4th step, I multiplied it by 4 1/2. So we can say that's 1/2 to the 4th. And if you do the math there, it's 1,000 times 1 over 16, and that'll give you the 62.5 that you got to by walking over, multiplying by 1/2 over and over. So what would the equation for this guess would be? Again, P of t, our number of rolls, would end up being 1,000 that I started off with, and then I kept multiplying it by 1/2, and I did that t times over and over depending on which second I was at, the tth second. So whenever we have this idea of we keep multiplying over and over by the same number, for each unit increase that we go in the input x, t, or whatever the variable is. We say that the data fits an exponential function, and that exponential function has form f of x equals c times b to the x will be the form, similar to the pattern that we just guessed for the previous two scenarios. So this would be like my c, and that would be like my b. This would be like my c, and that would be like my b, the piece that keeps getting multiplied over and over. So c is always going to be the initial amount that you start with, and this is also the y-intercept or vertical intercept of whatever graph you're looking at. And b is known as the growth or decay if it's going down, growing like it was in the coronavirus cases in the first scenario, decay like in the toilet paper rolls in the second scenario, and the key word there is factor. So whatever number you keep multiplying over and over or dividing, however you want to think about it, that's called the growth or the decay factor. So our first example, we just want to make sure we know the two pieces or the two components of an exponential function. We want to give the initial amount, the growth or decay factor, and then evaluate whatever we're supposed to evaluate with the function. So for part A, I guess I can think of this as 1 times 4 to the x. So I have an initial amount of just 1, I guess. I started with 1. And then since 4 is going to keep making my numbers bigger and bigger, that looks like it's going to be a growth. Let's go make a note of that over here too. If b is bigger than 1, we're going to have a growth. If b is less than 1 but greater than 0, we're going to have a decay. I should point out that in my exponential function, b is not equal to 1 and b is positive always, because if b is equal to 1, you keep multiplying c by 1 over and over, it's just going to stay a linear function. And b is always positive in an exponential function. So in this case, since the 4 is bigger than 1, we'll say that's a growth factor of 4. Then f of -2, that's no big deal. We just have 4 raised to the -2 because the input or the x is -2. That's going to be 1 over 4 squared, so that's just 1 over 16. So all we did was recognize what the initial amount or the c was, the growth or the decay factor, and then plug it in to the function and see what the output is. So why don't you go ahead and pause the video and try b on your own. Hopefully you had a chance to give that a try. So we'll say for the initial amount, we have 4 is what you started with. And then since the b is 3/4 and it's smaller than 1, we have a decay factor of 3/4 because my material is getting smaller and smaller. I also want to point out that you cannot multiply this 4 outside and cancel it with this 4 because that exponent is waiting to be applied to the 3/4 first. So make sure you do not cancel those 4 4s. Order of operations does not allow you to do that. So g of -2, no big deal. We're going to plug in 3/4 and find g of -2. That's going to create a reciprocal for my 3/4, make it a 4/3 squared. So now I have 4 times 16 over 9, and that's going to give me 64 over 9 for my output. Part C again, initial amount is 5, that's my C value. Then I have a 1.3 and that guy is bigger than 1, so again it looks like I have a growth factor of 1.3. In other words, I start with 5 and each time I go to the right, I multiply by 1.3 over and over and over. And this time we're evaluating 5 of √2, so we'll have to approximate using our calculator. So √2 is an irrational number about 1.41 or so. So let's go punch it into our TI. So we'll do 5 times 1.3 raised to the √2, and we're going to get approximately 7.25, let's say. I want to make sure that if you're not inputting it all at once, that you do the 1.3 raised to the root 2 first. If you're using a calculator that's not a TI, first you got to do the exponent piece, then take that answer and multiply it by 5. Make sure you do not multiply the 5 and the 1.3 again, because that exponent has to get applied first. Alright, so far we know an exponential function has form f of x, cbx, let's say, cb to the x, and we have an initial amount, a starting amount, and then a growth or a decay factor. Now, how do these guys look graphically? We're just going to use maybe we'll make an XY chart for the first two we look at, and then we'll use our TI to summarize the rest. So let's go do this one with an XY chart. So I've plugged in some numbers, some negative numbers, some positive numbers, and 0 in the middle, and those are the outputs I'm getting for my function. And if I go and I just quickly sketch that, I'm going to get at -2 something tiny like a quarter, at -1 a little bit higher at a half, at 0, 1, at 1 I'm getting a 2, and at 2 I'm getting a 4. And notice if I put if I go this way, even if I put like -100, I'm going to get 2 to the -100, which is going to be 1 over 2 to the 100, which is still going to be some positive small number. So even if I'm way out here, I'm still above the x-axis. Or if I go down here and put like 500, I'm going to get really big, right? I'm going to get 2 to the 500, which is going to be big, let's say. So if I walk all the way to the right, the thing keeps going up and up and up and up and grows and goes to infinity. So my graph looks something like that, but it does approach the x-axis and cannot become 0 or negative, therefore creating a horizontal asymptote at y equals 0. So as I go to the right, it's shooting up in the air, and on the left, it's getting closer and closer to the x-axis. That means the domain for this guy, I guess, is -infinity to +infinity. I can walk left to right and input any x's I would like. But for the range, I don't have any negative y values. I don't have a 0. It starts right above 0 and it goes up and up and up forever, all the way to infinity. Now that was a base bigger than 1 for a growth case. Let's go quickly look at the chart for a decay case when the base is less than 1. So notice I'm putting the same inputs, the same x values, and I'm kind of getting the reverse y values. A negative exponent means take the reciprocal of the inside, so 1/2 becomes 2 over 1, and when I square that, I just get 4. And go ahead and if you need to pause the video and make sure you got the same outputs for your y values. And I'm going to go ahead and plot these. So we've got -2 and 4, -1 and 2, 0 and 1, 1.5 in the middle, and then 2 gets me something even lower. And as you would imagine, like the previous case, as I go to the right, the values keep getting smaller and smaller, but never become negative or 0. And as I go to the left, they shoot up in the air. Again, you put negative values this way, you're going to get big numbers for your outputs. And if you put positive values this way, you're going to get small numbers for your outputs because you're taking 1/4, 1/8, 1 over 16, and so forth. And again, you're going to have also a horizontal asymptote at y equals 0. So for a growth case, as you walk to the right, you're shooting up in the air, notice. And for a decay case, as you walk to the right, you're going lower and lower. And the domain and the range happen, I guess, to be the same. I can have any inputs for my x's and for my y's, right from 0 on to infinity is what's going on. So essentially speaking, for a growth, you're walking up a steep curve, and for a decay, you're sliding down the curve on the other end. In the next video, we will analyze more graphs using our TI to summarize and generalize how we can guess what the sketch would look like, just depending on whether the base is bigger than 1, like the first example, or the base is smaller than 1, but positive, like the second example.